Okay, so I'd like to welcome everyone to the Mid-America Transportation Center Seminar Series. For those of you who have for background, we're the Region 7 University Transportation Center. We have funding from US DOT. Our focus is improving on safety in our region, which includes Nebraska, Iowa, Missouri, and Kansas. Speaking today will be Alexandra Kondyli. She is associate professor, and I'm trying to remember, Alexandra, how long that's been, but I think congratulations are in order on your promotion. At the University of Kansas, the University of Kansas has been a great partner with MATC for the past 14 years, and we're happy to have her here. She's going to be talking about modeling of driver behavior and aggressiveness using behavioral models, and I'm going to turn it over now. Welcome, Alexandra. I look forward to your talk.
Thank you so much, Larry. Let me start by sharing my screen. So first of all, I would like to thank you for inviting us to present this webinar. As Larry said, this is a project funded from the Mid-America Transportation Center. The project title was Modeling Driver Behavior and Aggressiveness Using Biobehavioral Methods. I was the PI of the project, and I'm with the University of Kansas. My co-PI on this project was Dr. Lila Krisikou. She's associate professor at the Department of Psychology at Drexel University, but she used to be with Kansas. And also Dr. Vishal Kummetha, who recently joined the Center of Urban Transportation Research at the University of Florida as a postdoc researcher, and he was the project manager. So I will start this introduction with this presentation with an introduction to the topic and the literature review summary. And I will also present an overview of the methodology and the data collection. Then I will hand it over to Vishal Kummetha, and he will present the major research results, our study conclusions, and as well as the study limitations and future research steps. And then we will open it up for questions. So mathematical models and tools of car following that currently exist, they lack behavioral components. Also, most of them are mostly descriptive in nature and do not really account for complexities of traffic phenomena such as the breakdown events. Consequently, significant calibration efforts are needed to match the observed variability with the model's outputs. In addition, the majority of these models are collision-free by default. Therefore, estimating surrogate safety measures through these models would not be very accurate. In our research, we hypothesized that we can borrow concepts from the cognitive sciences to enhance current car following models' ability to replicate field conditions. So these two research objectives were basically to establish a methodological framework that incorporates behavioral parameters to car following models, also conduct a driving simulator study and collect a variety of measures using subjective driving as well as biobehavioral measures, and lastly, to examine various constructs that to develop and also validate an extension to the intelligent driver model. Now, we selected the intelligent driver model, or IDM as it is known, because it's simple, but is also a very efficient car following algorithm that is used in our field. There's a variety of car following models that depending on the properties and the characteristics, we can basically group them into psychophysical models. And these are the Wiedemann model that, for example, we use in VISM. Another category is the stimulus response models, and the IDM is part of that category, or the variations of the IDM or the GHR model. And safety distance models, or else as we call them, collision avoidance models. And these include the Gibbs model that is used in VISM is included in this category. All of these models exhibit a variety of assumptions and levels of complexity and do not necessarily consider human factors beyond reaction time. In addition, researchers use classification methods to group drivers based on common features or characteristics. And in this way, they improve the accuracy of the driver behavior models. So to define these groups, researchers use driving performance parameters such as speeds or gaps and acceleration. They've also used demographic information or even behavioral traits such as cognitive workload and situational awareness. So it is very important to capture all of these parameters in our research as well. As I mentioned earlier, this study focuses on the IDM, and the equation of the IDM is shown here. The IDM predicts basically the vehicle acceleration as a function of the desired speed and the desired space headway. And it is applied to both car following and free-flowing situations. In addition, we borrow concepts from cognitive science, such as workload, situational awareness, and level of activation. So I'll spend a few slides to describe how we define these concepts here. For the workload, we use the definition that was used by Brockquist et al. And it says that based on this definition, workload is the proportion of mental capacity required by individual to perform a task. Workload can be measured using subjective techniques such as questionnaires, performance measures, as well as physiological measures such as changes to heart rate or changes to the pupil diameter. For situational awareness, which is our second human factors measure, we use the definition of Hensley. And situational awareness is defined as the ability to perceive, comprehend, and project future status of elements. So situational awareness has three components: perception, comprehension, and projection of status. Research has shown that there's a relationship between workload and situational awareness. If we have very high situational awareness with low workload, that means that the driver can very easily comprehend the information without requiring increased mental processing. And this is basically like an ideal situation. When we have low situational awareness, though, and high workload, tasks require more processing capabilities from the driver, and this means that some elements may be overlooked during the driving tasks, and maybe just one subset of those elements can actually be processed. Of course, this situation is not ideal, as we might have dangerous situations like crashes occurring. The third one that we use in this research is the level of activation. And this measure describes the driver's arousal or engagement before and during the driving task. The level of activation is not only affected by the primary task of driving, but also by secondary tasks, such as using the cell phone. It has been suggested to measure level of activation using electroencephalography device, or EEG, and using the 3 bands alpha, beta, and theta. So in this study, we followed the literature and we used 4 electrodes in the middle, those 4, to capture these 3 bands. The relationship between workload, situational awareness, and level of activation has not been thoroughly studied, but we know that the combination of high workload, low situational awareness, and low level of activation will result in poor performance. Whereas if we have high situational awareness, high level of activation, and low workload or processing, that might result in very good performance. However, we really don't know the expected performance for the remaining combinations between these 3 measures. In summary, Research has focused on workload and its relation to situational awareness, as well as driver performance, as well as how to measure workload. But the level of activation has not been studied enough with respect to these other two measures. In addition, with respect to car following, group calibration techniques that focus on behavioral and performance traits could improve the accuracy of these models. Now, the full framework of our research is shown in this slide. We theorized that the specific external conditions determine the complexity of the driving task. The capability of the driver, though, to handle the task mostly depends on their mental and on their physical characteristics. And this could be either static based on demographics or dynamic based on level of activation. We also use the driver capability task interface to investigate this relationship. And this is an interface that has been previously developed by Fuller. So we used Fuller's interface in our project. This interface says is that if the capabilities of the driver are greater than those required by the task, then the task will be completed easily. When the capability of the driver is sort of equal with the task demand, then the task starts to become difficult, and basically the driver is using all of the available capabilities to successfully complete the task. However, if the capabilities of the driver are less than those required by the task, then the driver will basically fail to complete the task. Now, the interaction between the capability and the demand can be quantified using the changes in workload and situation awareness. So if we have slight imbalance between workload and situational awareness over here, this can result in the driver compensating by basically adjusting their longitudinal control variables such as speed, acceleration, and headway. So for example, let's say we have a task that is a little bit challenging, that require increased workload. The driver might choose to reduce their overall speed or increase their headway in order to be safe, and also in order to maintain a comfortable level of situation awareness. This will lead to triggers. Trigger one that is shown here in this graph, to activate those that are activated through those small imbalances. However, if the imbalances between the driver capability and the task demand is quite high, then the driver will try to restore this imbalance, and this will result in both compensation and performance effect. So apart from adjusting the longitudinal control of the vehicle, we might have some lateral control issues as well. To simplify this framework a little bit, in this project, we study the interactions between all of these four measures: workload, situational awareness, level of activation, and driving performance. Of course, some of these have already been studied, for example, workload and situational awareness, as well as workload and driving performance. But a holistic look between these four will give us a better understanding of how car following is affected by this very complex relationship. Furthermore, we propose to capture the effects of this four-way relationship to the IDM by introducing a coefficient alpha, which captures both the performance and the compensation effects. And this performance and compensation coefficient is being applied to both the equations as it's shown here. This coefficient is calibrated based on actual driver data, which were collected in a driving simulator experiment. So the equipment that we used in our research is the KU driving simulator, which is an ADS mini-sim simulator enclosed in a half cab. It gives 170 degrees field of view. The simulator is also equipped with an eye tracker, 4VOFX3, which is able to capture pupil dilation and eye gaze duration. And we also had a heart rate monitor and the EEG, all of which were synchronized with a driving simulator. We use a total of 90 participants in this project, which is a big sample for driving simulator studies. And we split the participants in 3 groups age-wise, and they were equally split between males and females, as you can see in the table. Participants also received a compensation of $50 for their time. Now, all of the drivers had to drive 6 different tasks. And these 6 tasks had varying difficulty. So task 1 was basically the simplest task, and this was used as our baseline. Task 2 was very similar to task 1, but with slightly more traffic. Task 3 had more tracks, and also an inactive work zone was present. And task 4 had increased percent of tracks and more work zone activity. Tasks 5 and 6 had a higher density than the other tasks. And specifically in task 6, we introduced a secondary task. So during that secondary task, participants had to use an app like this one that is shown here. And basically in the app, they had to click the correct number that appeared in the screen. So with this, we tried to simulate like the driver trying to use their GPS system or any navigation system within the car, and basically taking their eyes off the road and to do that. We used a variety of data collection techniques. We got a rich data set to measure that, and in this way we were able to measure all variables of interest. We used changes in the heart rate. We also used the pupillary response and the index of cognitive activity that was measured from the eye tracker. And we also used the NASA TLX surveys that were administered during the experiment. All of these were used to measure the workload. For situational awareness, we developed a new technique that measures changes in time to comprehension via gaze overlay, and we also used the SART method. For level of activation, we use the EEG, the power spectral density. And for driving performance, we used variables, all of the variables that are basically collected in the simulator, such as speeds, accelerations, headways, standard deviation of lane position, and so on. We also collected a variety of data to group drivers based on their traits. So we consider speed, gap, and jerk values. We also used a very elaborate survey instrument to gather the behavioral traits, using surveys found in the psychology literature, such as the PANAS, need for recognition, CRP, neuroticism, empathy, psychological entitlement, and ethical dilemmas. Since we have so many different data and data collection methods during the experiment, the whole duration of the experiment was approximately an hour and a half long. So that I'll hand it over to Vishal to continue this presentation with research results.
Okay. Hi, good afternoon, everyone. Sorry, a bit of a technology problem there. Yeah, so I have control over the slides now. So just to quickly go over what we did, I'm going to reiterate a few things. I don't think I can still move the slides. Dr. Kondyli. Okay, so I'm going to start again right from here. just to make sure I go over a couple of things. The study itself was to model car following behavior, and we wanted to take into account how different drivers, if any of you have worked with car following, you know that we have a lot of calibration parameters that come into play. We adjust them relatively not knowing what they do. And the whole goal is, can we account for some of these calibration parameters and make the car following procedure, either calibration of these models, way more efficient than it already is? If I'm able to group a couple of drivers together and use one set of calibration parameters instead of calibrating each driver individually, this would significantly reduce the whole effort put into the process of calibration. So that was one of the goals. And we did administer a lot of surveys, as Dr. Kondyli said. And one thing I want to point out in particular is the cognitive reflection tasks. So these were a few mathematical questions. I think some of you have ever come across these. For example, if a lily pad takes 48 days to cover a whole pond, how long does it take to cover half the pond if it grows half size every day? So we administer such questions that they're rather intuitive, and if they kind of judge the aptitude of a person. So we want to see if their decision-making skills actually affects their car following behavior through such questionnaires. So then one other thing here is situation awareness. So Dr. Kondyli has talked a lot about situation awareness, but for this study, because situation awareness has always been measured in a discontinuous form, or it needs to be taken at the end of the drive, so we don't have a continuous measure of situation awareness. And for this process, we use eye tracking together with what we know as driver comprehension. So we administered different cue questions located during the drive, and these cue questions were to make sure that a driver comprehends to a situation. So for example, if you look at the first video on top, you can see that the cue question posed was, do you expect crossing deer? And we look for the fact that the driver has looked at the deer crossing sign, and we measure the time the green dot spends in any of these zones. So this gives you an idea of how each driver processes the specific information. And another example is this sign, where we have a variable message sign, and we're trying to see the driver read through the information and see how long it takes him to comprehend to what the sign says. Then we administer a probe question right after the cue is passed, and then we correctly calibrate the fact that he has comprehended to the sign. And we present a couple of these in each of our tasks, not a couple, we present 5 of these in each of the tasks, and we try to compute the level of comprehension for each driver. Now, overall, the technique used here also resulted in like 10.5% of false negatives. By this, I mean, for example, people with corrective lenses, it wasn't very accurate in predicting their measurements. So we tend to exclude those out of the charts that we created. But more on that in a few slides. But just to give you an overall perspective of how the workload changed, we can see the NASA TLX. It's a very prominent measure, highly validated to measure cognitive workload. And we can see that as our tasks got more complex with increasing demand, the scores on the TLX of all the participants increased higher. And keep in mind that all the tasks were performed randomly, so they were not repeated. The sequence of each task that was completed was completely random. So that's one thing to note. And the SART is a questionnaire that measures situation awareness. And you can see that as the workload increased, cognitive workload, the situation awareness scores decreased. And it doesn't happen, there aren't substantial increases for most of it for sequential tasks, but you can see the overall scale of this. And when we compare these to all the baseline tasks, you can see the significant p-values right there in table 1 and table 2. Okay, Now, we also plotted some driving performance, aggregate driving performance measures. For example, how does the average speed vary across these tasks? And what we see is that as the tasks get more complex, even if the traffic density or nothing particularly changed in the task, apart from the fact that they were just complex by nature with visual cues and a lot more situations like work zones, we can see a decline in speed on average. And this is very interesting because also the standard, as the speeds decrease, you can understand that the process of compensation is happening because they're competing, that we have tasks, the mental resources available to a person are competing due to the fact that the task is so complex. So we have reductions in speed. And we can also see some specific changes in lateral position. We have a slight decrease in lateral position followed by an increase when the distraction happened. So those are some key insights to how the thing was performed. And we looked at several other measures. We looked at gaze concentration and how gaze variability was affected. And we used this as a measure to predict some of our lateral positions for other relevant measures during the study. Just to continue, so a bit into the questionnaire data. What we noticed from the questionnaire data was some of the values were really interesting in the sense that any individual who reported some of the speeds that they follow in real life were actually were significantly correlated to the values we obtained from the simulator. So what that means is that although there was a 10% difference on average, what it means is that questionnaires could be a measure of, an accurate measure of how fast an individual can drive if we account for the 10% difference. So people on average report 10% less than they actually drive at. And we also see some other interesting findings that positive mood and extroversion. So if someone is in a happy mood, a very positive person, they're tending to drive at higher speeds, they experience lower cognitive workload, they're susceptible to more traffic violations, and they also have increased lateral position deviations, so they tend to vary off the lane quite a bit. So these were some interesting findings with the questionnaire based on the personality and what we saw in the driving study. And to continue, we did do a lot of time series analysis. So for example, I picked out one scenario of a participant, ID3, and for the most difficult task when we administered distractions through the application that you saw earlier. You can see the key locations when the distraction happened. So the blue arrows indicate the duration when the distraction happened, and the lateral position. So 0 indicates the center line of the driver. So the center line of a lane. And when it goes up and down, it indicates that there was significant deviations from the center line. So this, and that was an interesting thing, but as expected, if you're distracted, your lane position tends to vary too much. But also the same way, when we do the analysis, you see a spike in the heart rate. So we can clearly see that as the cognitive load increased, we see changes to heart rate. But again, this measure wasn't very sensitive across all cases. For example, you will still see normal heart rate in some places, and sometimes it's offset by quite a bit. But we had to run quite a bit of analysis to figure that out. And also we show some changes in level of activation just to throw it in for the time series analysis. Okay, so now based on all the comprehension scores we collected throughout the driving tests, we generated these really interesting plots of situation awareness where we can determine if a person is comprehending to a situation or to an object or to a cue just based on the flow of these charts. So when we ran the analysis, the Weibull distribution was the best fit for this model when we ran all the 200 or 300 events, because we had 5 questions for each participant for each task. So when we do plot these, we can see that as the tasks get more difficult the peaks of the test. So it takes longer for participants to comprehend as they're busy paying attention to other things going on in the task, for example, visual cues or the distraction that they were attempting. So the comprehension times increase. And however, this wasn't the case for task 3 and 5, which are kind of the offsets here. But again, these Weibull charts, the peaks represent the model values and the means are actually a bit off. But just to see what I mean, it took 25% of time to comprehend in task 3, which is pretty high for just one lane closed in a highway. But keep in mind that when we plot the velocities of these same tasks, so the speed at which the drivers were performing the task, you can see that task 3 was performed at a much higher speed than task 5 or 6. So this kind of gives you an idea of the interactions between what's happening in a driver's mind versus what we see in driving performance as these changes are occurring. Okay, so now to establish situation awareness, we normalize these charts, and any driver, say for example, spent 10% of the time looking at a queue, you could, and on a specific task, for example, let's take task 1, which is the blue one. If you spend 10% of the time around here, there's a one score allocated to him, indicating that he almost definitely comprehended to the task. However, if he spent about 5% of the time staring at something, there's only a 60% probability. So a 0.6 of a score was assigned to this driver. So that makes it more continuous, and we don't have to rely entirely on subjective measures for this. So as we continue, we developed this chart that gives you an idea of how the overall relationship. So as tasks got more complicated, we can see that the speed decreased. So there is a nonlinear deterioration of speed that is clearly observed, and there is also a nonlinear increase in the time spent gazing to achieve this comprehension. So this was one interesting finding from the study. Now, as we continue, this is the biobehavioral IDM, or the b-IDM, that we developed. And to develop this model, we had to group our drivers. So we first established our driver groups. As Dr. Kondyli spoke earlier, we used these specific parameters, so gap, jerk, and speed. And just to point out what jerk is the rate of change of acceleration or deceleration. So these measures are also commonly used by insurance companies to determine if you're a good driver or a bad driver. So we kind of fell back to some of these concepts, and we can clearly identify that driver A and group B has different types of drivers. You can see that a high score in jerk indicates that they tend to rapidly accelerate and rapidly decelerate. And out of the two, group A and B, you can see that group B are lenient to more on the aggressive side. So they travel at higher speeds, they follow smaller gaps, and they also tend to brake and accelerate really quick. And based on these, we use the cluster analysis to get to these values, and out of the appropriate ones, k-means was the most appropriate as we have the least significant values. And we also tried to keep our sample size split as evenly as possible. And you can see this chart that shows you how the different groups were established. And after establishing these groups, we come up with the variables that we use in the IDM for each of these groups, and tend to plot them across and tend to compare across the original IDM and see which one gives you better results and which one is easier to calibrate on the whole. So when we do establish these, We did develop, so if you guys remember, it was from the alpha that we had to look for, which was the parameter that we're introducing to the IDM model that takes into account all these different continuous measures that we developed. So we carried out several ANACOVAs, so analysis of covariances, and we did establish these significant measures. So interaction measures were also considered, but they didn't improve the model a lot. So we left it at this. And you can clearly, although the R squared is relatively low, we do have, these are behavioral models, and it's very hard to get a really high R squared because no two individuals are exactly the same. So you need to keep that in mind. And also we use the 75-25 data split. So we use 75% of our data to create these models and 25 to validate the models. And after we establish this, we can see that the same variables are actually significant in both drivers. So we have level of activation, situation awareness, workload as a measure obtained from the heart rate. So we saw that the workload as a measure of pupil dilation was not valid. And then it was a distraction present or a distraction. So that's it's a 1-0 binary value distraction, either 1 or 0. And then it also, car falling significantly depended on the lead vehicle's velocity, which is understandable because you're following a car, and if they reduce speed, we would also reduce speed. Okay, so these are that's the configuration. So alpha down here is a logarithmic equation, exponential in nature. Okay, and based on the validation plots, what we see is the simulator observed values are in black dotted lines, and the group IDM is what is just based on group parameters, and the calibrated IDM is the original IDM that has been calibrated to the best of our ability. And the b-IDM that you see down here in purple is the IDM that we use, that we developed. And clearly there's a very high correlation. Although the R squared was relatively low, the prediction of speeds was almost very accurate in this case. And as we continue, we can see that one thing that the b-IDM did not generate a significant amount was in the acceleration. So not a lot of changes were made in acceleration predictions, but you can still see that the peaks of the acceleration were better predicted. So lower accelerations are better predicted with the b-IDM than with the IDM itself. Okay, I think I lost. Okay, and then the trajectories also, you can see how accurately the trajectories of the drivers are being predicted by this new car following model based on the alpha parameter. And when we compare the goodness of fits for each of these values, so the calibrated, the group, and the b-IDM, we tend to see that the b-IDM has the closest relationship to the true values observed in the simulator, while the rest are somewhat over the top. And it also, we use two different measures, so normalized root mean square error and the mean absolute percentage error. And one of the limitations of the mean absolute percentage error is that lower, like small decimal values are highly exaggerated, and that we can see in these values with 150% higher. But you can see in this that acceleration doesn't change too much, but we substantially improve predictions of speed and trajectories based on this new IDM model. So overall, in conclusion, we developed different tasks over the simulator, which are actual tasks that we experience in driving. Not everything is less workload, and then we compare how the workload and situation awareness changes. We derived the fact that we were able to establish different types of drivers with the cluster analysis, and we proved that there are different types of drivers and they have different car following characteristics, and we could easily establish these parameters. The general form of the equation is there. We have no substantial improvements to acceleration. And we also saw that not entirely can the questionnaires be used as a substitute for driving performance measures. In fact, only for the speed as a fact. But for this study, since we depended a lot on the jerk rate, it should be taken into account that there's no way of predicting someone's acceleration and deceleration based on questionnaires. So driving performance variables are very helpful. So simulator data is always very helpful in calibrating this. And we did develop a discontinuous measure to measure SA, which hasn't been previously studied, and this is in the works. So we're about to publish the study, and we also saw that we were able to predict lateral deviations based on where someone is looking and their speed. And this has been published in Accident Analysis and Prevention if you need more information on that. And some of the limitations from this study is we assume a sequential change between, so if the workload changes, then the situation awareness changes, then this leads to a change in driving performance. However, this is not the case. They're all interacting. So once my speed drops, then my workload reduces, then my situation awareness improves. So a lot is to do with the interaction of these terms. And again, this study mostly focused on cognitive overload. So cases of underload, for example, when drowsy drivers or something that makes you sleepy or fatigued drivers hasn't been examined, and that should be another part of car following. Also, this is entirely based on the task capability interface developed by Fuller. There are several other interfaces that could be established, that have been established, that could be used as well to change the study. And behavioral questionnaires, whatever we administered, we had to administer them a few weeks or sometimes a month before the driver actually appeared for the study. So this kind of created a lag between the interpolation of the results. And maybe if we had about 6 hours in this driving simulator room, we could do a direct correlation there. But again, it's impossible to keep people for 6 hours. Also, the transferability of simulator results. So this is always a concern that we're not sure how well the results can be transferred to real life trajectories, but we hope to do more work in that area. And yeah, so future research, we suggest implementing naturalistic driving studies. We're going to try and implement the b-IDM to simulation models and see how it affects traffic flow and if something can change for that. And also an extension of the framework, so partial automation and that. So that's it. I'll open the floor to any questions. Feel free to speak through it. I saw one in the chat. Let me just open that. There's a question by Jay. I see regression model, several components are very small. Feel free to talk through the microphone if that's allowed, Janet.
Sure. Just a quick question on your regression model. You had several terms that are multiplied together. Many are raised to exponents based upon your fit. Many of those exponents are very small.
Yes.
I don't know what the magnitude of LA is, but won't that force that term to be essentially something close to zero?
No, exponent to a negative value, right? So technically what happened is we just combined a whole bunch of continuous data, and we're looking at several time series values. So if I excluded the value of level of activation from this model, although it would cause a relatively small change, but it's still enough to have a relative power of 0.5. So if that makes sense.
Okay. Thanks.
Yeah. So we have the powers right there. So yeah.
Okay.
Great. Any other questions?
Hello. Can you hear my voice?
Hello. Yes, go ahead.
Oh, okay. Sorry, I was on the road, so I just feel like it was very interesting of this topic because I had a similar study last year. So I just stopped on the roadside and asked a question. I'm not here. Probably I'm not here clearly, but I would like to ask about so you have 3 groups, like between groups when you design the experiment. And what did you find in terms of those ages, like different drivers? Or did you group drivers in terms of their driver experience?
Okay, so we did group them in terms of age at first, but we don't see any significant differences to car following with respect to car following for age, or even in their behavior with jerk rates and speed and all this. So we did consider age as a variable, but we just don't report it here. But yeah, we didn't see any significant differences with the age.
Okay, great. So I was working with DocRelate, and we did an experiment in the field, and we had the mobile phone games as a distraction, as a secondary task for drivers, and we were testing drivers' response when there's an emergency in front of the vehicle, and we grouped 2 types of drivers: experienced drivers and novice drivers. So within 5 years driving experience, which were novice drivers. And then we found that experienced drivers will react, or they were less distracted by the situation awareness, similar as what you did. We were testing drivers' skin conductance and heart rate and respiration, those kind of parameters. So, and we did find that the speed is kind of associated with drivers' distraction, and if you have a heavy task for drivers, they may slow down accordingly. So yeah, I feel like very familiar with, you had a very small R square when you do the linear, and your sample group is large, even though you have 3 groups. Because when I did the field test, we only have 20 participants. Yeah, so sure. I totally understand that a low R square and the coefficient and power of that experiment.
Yes.
Yeah, just want to add on to that. Yep. Mm-hmm. Okay,
sure. Yeah.
Great work.
Thank you.
Yep, thanks.
Thanks. Any other questions? Well, I guess the questions are over.
Well, thank you so much,
Alexandra. It's great seeing you for the first time, Janet.
Yeah, you as well. So
thank you so much.
Thanks.